Here, where it's very interesting, they're actually more sophisticated than you think, those robots. They have a lot of sensors. They can be phototaxis, chemotaxis, magnetotaxis, electric field, oxygen level. Example, aggregate. We need to stay together there. Stay together to go somewhere because when they deliver the drugs there. Then they said, okay, shut down it to magnetotaxis, aerotaxis. I want to know the 1 or 2% oxygen level. That's what happened. They form a ring over there because of the drop of water. And then they expand it as it's stuff like that. So you can exploit the sensors actually. And if it's like a tumor, stuff like that, the oxygen level will change. I have to stop there. Here I want to show that we can build different structures of those bacteria. 3,000 bacteria build a M shape. I cannot show you the movie because I'm over. To convince people that bacteria could actually deliver drugs somewhere, we have I have a video where we built an ancient pyramid in 15 minutes under computer control. I cannot show you.
Yeah, we can see the video.
You saw the video?
Yeah, we can go into the question time.
Okay, and yeah, okay, so we go to question times. Here we go. And so what I want to say here is those bacteria, just to finish it, those bacteria, they're very good at microvasculature, but in the larger blood vessel, the thrust force, which is 4 to 4.7 piconewton, they're not strong enough. So right now we encapsulate, in the other technology developed by other carrier, we encapsulate those bacteria to release them very close where they're more effective. And it looks a bit like what NASA is doing. Actually, the astronaut can be the bacteria and the release and stuff like that, right? And this is what I show over here. So thank you very much.
Okay.
Yeah, sorry about that.
Oh, no, Sylvain, it's no problem at all. So Dr. Martel seems to be on the same wavelength with Dr. Blumberg in terms of the fantastic voyage. We have about 6 minutes for questions. Yes, please.
I wonder.
Please announce yourself again because each presentation is a separate video. Right, they may become
separated. Yes. Yeah. Steve Lee, OSU. And I wonder if you could comment, you're talking about magnetotaxic bacteria, and if I remember correctly from bacterial physiology, the mechanism by which chemotaxis works, and presumably also magnetotaxis, is that the flagella are rotating in one direction, and then they have at some frequency, they change direction, the flagellar bundle flies apart, and they stop providing motive force. Right? And the mechanism by which chemotaxis works is that as you move up a gradient, the occurrence of that, the change in direction and the flagella flying apart and your loss of motive force, that frequency drops, right, as the gradient increases. And so they tend stochastically to migrate towards whatever it is they're attracted.
By which frequency are you talking about?
So frequency of direction change of the flagellar.
Oh, yeah, right, yeah. Well, this is something about advantage of magnetotaxis compared to chemotaxis. It's true the flagella will change to... and it's a random thing, which is not good in the engineering point of view. Magnetotaxis is... it's a bit the same thing. Those try to find the oxygen gradient 1 or 2%, and they will reverse it, so they don't turn around. They reverse the flagella to maintain into this gradient, stuff like that. Now, they're sensitive to 0.3 to 0.5 Gauss. 0.5 Gauss is the Hertz geometric field, you know. If you increase slightly to 1.5 to 2 Gauss, which is almost nothing, you know, to generate, it's very low power. Then the other component, chemotaxis and aerotaxis, become negligible, and they will not rotate it. They will go, actually, we send to oxygen gradient or some zone where they're going to die, and then we maintain it. So tell you how they obey. It's a suicide mission, and they go exactly where we want it to go. And so they don't have this reverse stuff like that. In the case where you have a very low magnetic field, 0.2, 0.5, yeah, this is true, they will reverse because other factors will influence that. But if you boost a bit the magnetic field, other component, they don't do it. They just go exactly where you want to do. Now, if we attach to big particles, stuff like that, they find out instead of pushing, they go around, it's not effective, it will reverse it to pull the object. I have a video, I didn't have the time to present that. So there's some situation where they go reverse or forward. We don't know everything, we know some what they do that, so we exploit that sometimes. But in this case, if you increase about the 2-3 Gauss, they will not have this reverse of the molecular motors.
So where I was going with this is that I was wondering, it was like everything we've seen so far is an operator directs, right?
Yeah.
And so do you envision a system where basically the nano robot itself has the capability to migrate up, say, a magnetic gradient, right? Without the direct involvement of an operator?
That's right. Actually, what we're doing right now is that we develop another platform just next to MRI with using registration techniques. The problem is at this small scale, MRI doesn't see the blood vessel. Now, we study how those bacteria react to different obstacles, and we transfer the control to this biological bacteria. And what we found that if we modulate a certain thing like that, we increase the chance of those things to get to the tumor. So pretty much it's like an instinct, when we tell them that the food or whatever is there, and they find a path to do that.
And they will intrinsically make their way to
they do that. I didn't have time to show that. Actually, it doesn't work with one bacteria. If you have a swarm, enough population, as soon as one finds a way, most of them will follow there, and they maintain together to deliver that. So because we cannot control that at this scale, because the imaging modality doesn't allow us to see the route. We can see the target, we can see where they are, but we don't see in between. So when we get to microvasculature, now we study how they behaved, we exploit that, and we help them knowing some information about the microvasculature. We have some models that, but we don't know exactly the blood vessel. We mix that together, and then we increase the chance to those bacteria to that. Not 100% get there, but we try to use biology, if you want, those bacteria as a controller, but mixed with all this big platform around it to increase the chance to target it.
Dr. Martel, maybe instead of further question, if you want to show the video, it could be, if it's easy for you to show, it could be helpful to illustrate what you are describing. And you could also talk to us about.
I got here, for example, this is a microvasculature, we don't see it, right? It would be like having I made a video I didn't show there. But it will be like, okay, if you have this artificial device, you don't know where it is. If you happen to if you happen to be aligned, that's fine. But if you have something artificial, you get there, then you don't know where to go. Now, if you have many of those bacteria, and so there's a chance that one find a path over there, they don't get stuck in that, and the other one would follow them, okay? And it's pretty much what happened. I mean, this is a very simple video there. But this is 20 microns about the vasculature human. I have another one on 4 microns, the smaller vasculature. So the B is the magnetic field that we just say, okay, we get out of here. This is 20 microns. This is a big wall to make it more difficult there, right? And then we just orient over there. We don't know exactly where it is, but, well, there's some, because this is a lab on chip, but you can see most of them will follow the path and stuff like that. But we lose some bacteria for sure. It's not 100%, but we try to increase the amount of stuff like that. There's still more work to be done because we don't understand all the behavior of this thing and exactly the interaction between the bacteria and what's the minimum population that we need, stuff like that. Yeah. But that's a general idea. Yeah.
Okay, thanks. One last question.
Yeah, just real quick. The idea behind this is is what you want to try to do is get your particles in there so that and then self-assemble them and to do something once they're there. And that's your benefit over just regular nanoparticles that have antibodies on them that people can already get to go to different targets.
Yeah, right.
And
Yeah,
stuff
right.
like
The idea is that instead of a huge quantity that can end up at different location, it's to boost a bit instead to go point A to point B, and over there rely on what is done on the.
So you're not looking to actually deliver something in and have them self-assemble into a more complex behavior. What you're trying to do is just lessen the
like I said, we're just carrier. I mean, you put whatever you want. It's nanoparticle, can be anything. We have developed antibodies. We attach to it, we encapsulate it, we deliver it. Whatever it is. Whatever it is. We're not on this business because we're engineered there, right? So we just go point A to B, and then how effective the drug is and stuff like that, I mean, I don't know. It's just a track and you load whatever you want there. So we try to make it as general as possible.
Thank you. Thank you very much.